Entropy Made Me Do It, Pumps, Nozzles, and Other Second Law Shenanigans, Part 2, is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. These videos, Entropy Made Me Do It, Second Law Shenanigans, Part 1 and Part 2, derive the equations for the application of the second law of thermodynamics to common items in power and refrigeration machinery. Part 1 discusses the turbine or the expander, the adiabatic compressor, and the isothermal compressor. Part 2 discusses the pump, the nozzle, and the valve or throttle. The third piece of equipment, first in this video, we're going to discuss is a pump. We are only going to deal with pumps that pump liquids that we consider to be incompressible. The inputs to a pump are typically specified as a mass or mole flow rate, the inlet temperature, and the inlet pressure. The outlets are typically specified as the same mass or mole flow rate and the outlet pressure. The purpose of a pump is to increase the pressure of the fluid. Pumps require work, so we have to have shaft work or power going into the pump. The fourth device we're going to look at, second in this video, is a nozzle. We have two nozzles displayed here. One is a converging nozzle, like you might find on a garden hose, and the other is a converging diverging nozzle, like you would find on the exhaust of a jet engine or rocket engine. The inputs to a nozzle are typically specified as a mass flow rate, an inlet velocity, an inlet pressure, and an inlet temperature. The outputs are typically specified as the same mass flow rate and an outlet pressure. The point of a nozzle is to increase the velocity of the fluid. Finally, we have a valve, a throttling valve, an orifice, or a similar device. These are referred to as throttling processes. In a throttling process, you typically specify an inlet mass or mole flow rate, an inlet temperature, and an inlet pressure. The outlet, you typically specify an outlet flow rate, which should be the same as the inlet, and the outlet pressure, which is substantially lower than the inlet pressure. Up now is the pump. A pump is typically used on a liquid as opposed to a gas, and is designed to increase the pressure of a largely incompressible fluid. The one on the right is a model of a vane pump, and the one on the left is the model of a peristaltic pump. Peristaltic pumps are often used in biolabs or similar things for positively displacing exact small amounts of liquid. A real pump has a pump efficiency that compares its performance with that of an isentropic pump. The pump efficiency again is the isentropic work divided by the actual work, because you have to put in more work to increase the pressure of something in the real case than you do in the isentropic case. It's also the isentropic change in enthalpy divided by the actual change in enthalpy. We're going to do a little formula manipulation here to derive the final result. You don't need to be able to replicate the steps, but it's nice to see a derivation occasionally, and to see that there actually is fundamental foundation to thermodynamics. If we start with the fundamental property relationship that we derived in an earlier video, we get that du hat is equal to TdS hat minus PdV hat. If you recall, this came basically from U equals Q plus W. If we take the differential of H hat equals U hat plus PV hat, we get that DH hat equals DU hat plus PdV hat plus V hat dP. Rearranging and solving for du hat, we get that du hat equals dH hat minus PdV hat minus V hat dP. Continuing with this brief derivation, we have dH hat minus PdV hat minus V hat P equals TdS hat minus PdV hat. And if we simplify this, we end up with dH hat equals TdS hat plus V hat dP. Now we will use our second law for an adiabatic and reversible or isentropic pump. Delta S equals 0, which implies that ds hat is also equal to 0, and finally that dH hat equals V hat dP. As we discussed, when treating liquids as incompressible, the volume of a liquid is a very weak function of pressure, unlike the volume of the gas, which is a very strong function of pressure. We take the integral of dH hat, which equals the integral of V hat dP. Pulling the V hat out, we get V hat integral of dP. And finally, the isentropic change in enthalpy is equal to the isentropic work, which is equal to V delta P. As before, we calculate the actual work in the pump from the actual shaft work is equal to the isentropic shaft work divided by the efficiency of the pump. Likewise, delta H hat actual equals delta H hat isentropic divided by pump efficiency. If necessary, you can go back and use some of the other fundamental relationships that you can look up to calculate the entropy change for the actual pump. I don't recommend doing so when you're doing introductory level work. Our next device is a nozzle. On the left, you see a typical brass water nozzle, like you'll find at the end of a garden hose. And on the right, you see a de Laval nozzle, or the sort of nozzle you'll find on a rocket engine or a jet engine. The first one is a converging nozzle, and the second one is a converging diverging nozzle. You can use thermodynamics to explain the reason for a converging diverging nozzle when you have a compressible fluid, such as a gas. But we're not going to derive that here. Wikipedia has a fairly complete description of a de Laval nozzle. For the nozzle, we're going to define a nozzle efficiency similar to the efficiencies we define for other devices that compares its performance with that of an isentropic nozzle. The nozzle efficiency is based on the kinetic energy of the exciting fluid. It is the velocity squared out for the actual nozzle divided by the velocity squared out for an isentropic nozzle. I don't know why the expression doesn't include the initial velocity squared, which is what I would have done. The point of the nozzle is to get as large as possible increase in velocity. We're going to begin again with the first law of thermodynamics. This time we have delta H dot plus delta EK dot equals 0 because we're going to assume that the nozzle is isentropic, so there's no Q and that there are no moving parts in the nozzle, so no shaft work. Splitting up, we have h hat out minus h hat in plus u squared out over 2 minus u squared in over 2 equals 0. You will notice that we switch from a total to a specific basis. We can then solve the first law for the velocity squared out, and that's equal to 2 times the change in enthalpy. Notice that's in minus out, not out minus in, plus the initial velocity squared. It's quite a frequent approximation to consider the velocity in to be 0, or close to it, which may explain the efficiency definition. Solving for the actual outlet velocity, we get the square root of 2h hat in minus h hat out plus u squared in. You need to be very careful with the units on these sorts of expressions. For example, if you are using an ideal gas, the enthalpies are likely going to be on a per mole basis, and the velocity is going to be on a per mass basis, so you will need to convert back and forth and track those units very carefully. Professors who are really cruel will sometimes throw BTUs in there, which have to be converted to foot-pounds at some point. Since we know the enthalpy in, but not the enthalpy out, we're going to have to use the second law to get the enthalpy out. Delta S dot equals 0 for the isentropic case, which means S hat out equals S hat in. If we're dealing with an ideal gas, then delta S hat equals 0 gives us our usual C sub P log T out over T in minus R log P out over P in. As we've done before, we can solve that to get T out over T in equals P out over P in to the R over C sub P power. We can substitute in that expression for the delta T in our enthalpy relationship. Delta H hat equals C sub P delta T again. We're assuming that C sub P is a constant and not a function of temperature. We have C sub P T out minus T in. Then substituting in our earlier expression, we have C sub P T in times P out over P in to the R over C sub P power minus 1. And finally, we end up with our result that u squared out is, in the isentropic case, minus u squared in is minus 2 C sub P delta T, which is 2 C sub P T in times 1 minus P out over P in to the R over C sub P power. Again, watch out for your units in this expression. We can also solve this expression with steam. For steam, you want to find the value of enthalpy in the steam table as the same entropy and pressure as the outlet. Once you've looked through your steam table and found the value, then you can plug into the expression. So you have u out isentropic equals the square root of 2 h hat in minus h hat out plus u squared in. Again, be careful with the units. The steam table is in kilojoules, and you probably want units of joules. Then, once we've found the isentropic velocity, we have to find the actual velocity with the efficiency. So the actual velocity squared is going to be the efficiency times the isentropic velocity squared. Don't forget to take the square root at the end. The actual velocity is lower than the isentropic velocity. If necessary, you can calculate the actual temperature, the enthalpy change, and the entropy change both for the steam and the ideal gas cases, but usually there is no reason to do so. The final device that we're going to look at is a valve. We're going to consider a partially open valve that is restricting the flow and dropping the pressure, an orifice or an opening that is deliberately placed to drop the pressure, or a throttling valve, which is found in just about every vapor compression refrigerator because it's much cheaper than using an expander. And sometimes you'll even see a porous plug in a pipe. All of these can be described as throttling processes. The picture on the left shows a partially open valve, and the picture on the right is a throttling valve for a refrigeration system. In deriving the first law for a throttling process, we have to consider that a fluid passes very quickly through the valve and doesn't have time to transfer heat with it. Therefore, we treat the heat transfer as being essentially 0. The first law then becomes, starting with the original delta H dot plus delta EK dot plus delta EP dot equals Q dot plus W dot shaft. For a throttling process, delta EK dot is 0, delta EP dot is 0, Q dot is 0, and there is no shaft work. The result is that enthalpy out is equal to enthalpy in. A constant enthalpy process is called isenthalpic, which sounds remarkably like isentropic, but is not. There really isn't much to do in analyzing a throttling process for an ideal gas, since the enthalpy is a function of temperature, and delta H equals 0, so delta T equals 0. For a real gas, however, you have something called the Joule-Thomson coefficient, which becomes very important when doing things such as liquefying gases. The ideal gas result of delta H equals 0 and delta T equals 0 is that P out times V hat out equals T in times V hat in. And since the point of the throttling process is to reduce the pressure, that means that the alkali-specific volume is going to increase. Well, where do you find throttling processes? As mentioned, you will find them quite frequently in a refrigeration cycle or a vapor compression cycle, which we will study a little later. In a refrigerator, you start with a liquid at the edge of the two-phase region that you have just finished condensing your condenser. So, a throttling process for a liquid at the edge of the two-phase region is much more interesting than an ideal gas case. Normally, one specifies the inlet temperature and the inlet pressure, and that the quality of the incoming fluid is 0. We also specify the outlet pressure. That gives us H hat out equals H hat in. One then uses the fluid two-phase table to determine the final pressure and quality. Since we haven't looked at other refrigerant tables, we will look at steam for this example. For example, if you take saturated liquid water at 50 bar and flash it to 1 bar, then you will end up with a two-phase mixture of liquid water and steam. In our case, we want to calculate the final temperature and quality. You might have noticed earlier that a throttling process is used to flash a high-pressure multi-component mixture in a separation process. Looking up in the steam table at 50 bar and at 263.94 degrees Celsius, we find that H hat in is equal to the H hat of the liquid in the two-phase region, and has a value of 1154.5 kilojoules per kilogram. We then look in the steam table at 1 bar, which is our final pressure. The temperature out is 99.61 degrees Celsius. H hat of the liquid is 417.44 kilojoules per kilogram, and the H hat of the vapor is 2674.9 kilojoules per kilogram. Just for fun, we'll notice that the enthalpy of the evaporation is 2257.5 kilojoules per kilogram. Plugging in with the H hat out being the same as the H hat in, we get the quality is 1154.5 minus 417.44 over 2674.9 minus 417.44, or over 2257.5, which works out to be 32.65%. When using a throttling process in a refrigerator, the point is to keep the quality as low as possible while cooling as much as possible. The throttling process is extremely irreversible, so we don't calculate an isentropic efficiency. For almost all small refrigeration units, the designers accept the large irreversibility because a valve is much cheaper than an expander or a turbine. Throttling into the two-phase region is essentially a flash calculation accounting for the mass balance and the energy balance. The takeaways from this video are: 1. Pumps and nozzles all have efficiencies that compare the real or actual case with the isentropic case. 2. Valves or throttles have such large irreversibilities that no efficiency is calculated. 3. We modeled pumps for incompressible fluids only. 4. Nozzles and throttles were modeled for both steam and ideal gas. Thanks for watching. This video is brought to you by the DOFPro team.